Hey, it's Dr. J again. Continuing the lectures on limits, today we're going to get into the algebraic methods of determining limits. So yesterday, or in my previous video, whenever you watched it, I spent an exhausting amount of time completing tables numerically. So before I started this video, I spent probably about 20 minutes filling out these two tables for two different functions. Today we're going to be talking a lot about how to incorporate algebra and combinations of functions. So when we have more than one function, the classic names that we use is f and then g. And if it becomes necessary, we might need to drum up some other names like h or j or what have you. But generally speaking, at this level, two names is enough. So we have the function named named f, and then we have its counterpart here, g. They look very similar. They are very similar in nature. I just made a slight modification to the middle term in the denominator and the last term here. The reason why I want to show you this is today's lesson is going to be all about algebra and how to use algebra to avoid doing all of this. So I'm hoping that unless it becomes absolutely necessary, which it might, where there's a problem where we just can't quite get our head around it algebraically, we still have the numeric method at our disposal if necessary. You could probably guess that I am interested in the limit near 5. Okay, if you plug 5 into the function, let's try f. Let's see if it's in the domain. We get 5 minus 5, and then we get 5 squared minus 9 times 5 plus 20. So we get 0 in the numerator. All right, now that's not a problem. 0 in the numerator is fine. Let's see what happens in the bottom. We get 25 minus 45 plus 20. And there's the problem. 25 minus 45 is negative 20, and then plus positive 20 gives us 0 in the denominator. So if there was a 0 in the numerator, but not in the denominator, that would be okay. Then the value would exist, right? It would just be 0. But if there's a 0 in the denominator, this is dne, yeah? So that means that f of 5 does not exist. All right. So we can't simply insert 5, so we're going to take a limit as x approaches 5 from the left, which I've already done a lot of the calculation for you. So I did all of that on my calculator by inserting 4.9 into this function and calculating it all out carefully and putting 6 decimal places. You can go more. Some of the problems allow less, but 6 is a good place to stop here. And I think you can clearly see 1.111, 1.010101. You see the pattern? 001, 001. This next one would be 0001. And then even though I truncated it, it actually continues that pattern, 0001, 0001, etc. And you can assume that these are going to just keep increasing the number of zeros until they're all zeros, and so the limit from the left is 1. Yeah. Similarly, when we do the limit from the right, so approaching from the right, it's 0.909090, 0.990099009900. See the pattern? 9990000, 9990000. Pretty distinct pattern here. I have to admit that when I was doing this, I double-checked most of them because I really wanted to make sure I didn't make a mistake. But once I recognized the pattern, I put my calculator down. In fact, we might not even need it today. And I just did it using pattern recognition. So that one looks like it's also, if you go long enough, if you made a big enough table, it would go 999999999, which is again approaching 1. So because these agree with each other, I'm not going to draw any more arrows. I'm just going to draw it right here. We can now remove the plus and the minus sign and just say limit as x approaches 5 of f of x is in fact 1. All right. So the limit from the left equals the limit from the right. And since those are equal, that means the limit exists and it is equal to 1. All right, so while I was talking, you might look at its counterpart here, g, and say, well, you look very similar, right? Very similar. And again, if you plug in 5, you're going to get 5 minus 5 in the numerator. 5 minus 5 in the numerator. That's, again, 0. That's not a big deal. All right, let's see what the bottom comes out to be. 5 squared minus 50. 10 times 5 plus 25. So that's going to be 25 minus 50 plus 25, which is, again, 0 over 0. So because we have 0 in the denominator, that means that this value does not exist. All right, so again, 5 is not in the domain of either one of these functions because it causes the denominator to be 0. All right, so let's go ahead and do the same thing. Let's find the limit as x approaches 5 from the left. This time it's of the function g of x. And look what happens. 10, 100, 1,000, 10,000. The next one, if we kept building a larger table, would go 100,000 and 1,000,000 and so on and so forth. So that means the limit does not exist. All right. We can't say that it's equal to infinity, but we can say it approaches infinity. Okay? It's approaching infinity. It makes me want to double check. I think it's supposed to be negative infinity. I think one of these is supposed to be negative. Let's double check. Let's just do one of them. The top one will be the, if the first one is negative, then they're all negative. So we got 4.9. I'm going to do the denominator first. Squared minus 10. It is negative times 4.9 plus 25. Yep, and then 4.9 minus 5 is negative 10. I apologize. I'm glad we caught that now. So it's going negative 10, negative 100, negative 1,000. See, I kept my calculator around just in case I needed it. So all of these values are negative. Negative 100,000. The next one will be negative 1,000,000. So the limit does not exist, right? It's not approaching a single real number as it is over here. But we can say that the limit, we can describe the behavior by saying the limit is approaching negative infinity. The limit from the left. All right. I did not make a mistake on this side. This side is all positive. All right. I think when I was writing it down, I just got a little overzealous there. So the limit as x approaches 5 from the right, again, 10, 100, 1,000, 10,000, 100,000 is again dne. So we can't say it equals infinity, but we can do a similar thing, and we can say the limit as x approaches 5 from the right approaches infinity. So it's getting closer and closer and closer to infinity. It's getting larger and larger and larger. But it's never going to become a single real number, which is what it has to be in order for the limit to exist. So this is the limit from the left. This is the limit from the right. These do not agree with each other. All right? I mean, even if they did agree with each other, even if they were both infinity or both negative infinity, technically the limit without the plus or minus, just the general limit, is still dne. All right. And so I briefly mentioned this in the last video. This is sort of just a warm-up to what we're going to be doing today. We're going to be continuing to discuss limits, but we hope that we don't have to draw these tables. In fact, I'm going to erase them, and hopefully that'll be the last table that we see for a while. All right, and then I'm going to talk a little bit about what this means. Since f of 5 is dne, and the limit as x approaches 5 exists and is equal to 1. Yeah. Once I give you a number, I usually just say it exists, but I don't bother writing the word exists, right? However, when it doesn't exist, I want to say dne does not exist. The point, there is no point at x equals 5. Instead, it's a hole. Or an open circle. That's the notation that we use for a hole. So something like this. I only need quadrant 1 for this. I don't need the rest of the quadrants. So I've got 1, 2, 3, 4, 5. That's my x-axis. The limit is 1. So there's a hole right here at 1. And then the graph is, something like that. I only know what its behavior is near 5. I have not explored the rest of the behavior. So I know that there is a function, I know there's a hole, and I know that there is no point at x equals 5. So there's no solid dot at x equals 5. This hole is sometimes referred to as a singularity. It's a fancy way to say a hole. But the limit exists. As you approach it, you're getting closer and closer to the hole, but you'll never actually hit the hole. Let's compare that to its friend here, or its counterpart, g. Since g of 5 is also dne, g of 5 is also dne, and the limit as x approaches 5 from the left is negative infinity, and the limit as x approaches 5 from the right is positive infinity. So if either one of these limits is infinity or negative infinity, either one, you have two possibilities. They could be reversed, and this property would be very similar. X equals 5 is a vertical asymptote. I'm thinking ahead, we're eventually going to do horizontal asymptotes, but today we are doing vertical asymptote. So that's that dotted line that I referred to. So we hope, moving forward, that we can discover all of this same information by learning some new properties of limits. So 1, 2, 3, 4, 5. Again, this is my x-axis. I've got x equals 5. All right. And then there's a dotted line. Now, again, on a computer, it's traditionally not visible unless I, use some special code to highlight it. But if I just typed in the function, the it would just be, you just wouldn't see any points along this line. This is dotted line. It's equivalent to an infinite series of holes. Yeah. All right. And then so as you approach 5 from the right, oh, shoot. I actually need the other quadrant for this one. I need the other quadrant because it's going to negative infinity. So you have this asymptote at 5, x equals 5. And as you approach it from the left, the graph is going down, sort of like this. And then as you approach it from the right, the graph is going up, like that. And again, I don't really know what's happening away from 5. I mean, I've seen these graphs before, so I mean, I know, but the information that we have so far doesn't really tell us that. I did draw one of these pretty clearly in the last example, but this is the general shape of the function. It's not the best one I've ever done, but that's sort of the general idea. As you approach 5 from the right, it's going up. That's positive infinity. And as you approach it from the left, it's going down to negative infinity. All right, so all of this could have been done in the previous video, but I just wanted to show how to end the practice of numerical analysis, of plugging in numbers for every function, and introduce you to the world of algebra today, where we can hopefully come up with all of the same type of results without needing to exhaust ourselves with tedious calculations. So how are we going to do that? All right, well, first thing we're going to do is erase this, say goodbye to these two graphs. And then I'm going to introduce a set of properties that we should carry with us throughout the course. So these are your properties of limits. Okay. So in order to exercise these properties, we first need two functions. I'm using the short notation of just f and g. Where the limits exist. C is a constant. You can't see that. So f and g are functions. C is a constant. Yeah, also known as a real number. And the limits exist. Now again, if a limit exists, I don't necessarily have to say the word. I just have to give it a number. Yeah, L, a real number. Okay. So not infinity or negative infinity, like I just demonstrated. So a number, 1 or 1/4 or 2.7 or whatever, some kind of real number. And the other limit also exists. All right. right? So m and L are both real numbers, which means both of these limits exist. Then we have 9 properties. There are 9 things that we can assume. I don't know if I'm going to be able to fit all 9 of them. I sure hope so. The limit as x approaches c of a constant k is just equal to k, where k is a constant. So it's not a variable. Number 2, the limit as x approaches c of x is just c. X is a variable. We call it the independent variable. I wrote INDY for short. So I want to make that very clear. K is not a variable. K is just some constant. But x is, in fact, a variable. All right, number 3. The limit as x approaches c of f of x plus g of x is equal to the limit as x approaches c of f of x plus the limit as x approaches c of g of x. This can sort of be thought of like the distributive property in algebra. Right? You are taking the limit and distributing it over the sum, and now you have the sum of the limits. So the way I memorize this, because I'm a sort of auditory learner, I like to close my eyes and just memorize the way things sound. So this is the limit of the sum is equal to the sum of the limits. The limit of the sum is equal to the sum of the limits. Now, since we know what these limits are, those are real numbers, we get a nice real number answer, L plus M. Fourth property, well, it's very similar. The limit of the difference is equal to the difference of the limits. When I was in college and I was trying to save paper or save writing, I would combine 3 and 4 together and just say plus or minus. Yeah. So the limit of the sum is the sum of the limits. The limit of the difference is the difference of the limits. And again, because these limits exist and we know that they are real numbers, this is just L minus M. Okay. Let's see if I can squeeze in one more before I have to erase. Number 1 is a constant all by itself. Yeah, just limit of a constant is just equal to a constant. All right. I'll explain this in more detail when we see some actual examples. So this 5th one is a combination of a constant and a function. It doesn't really matter which function you use. I'm going to use f. So you have a constant multiplied by a function. Sometimes we omit the dot and we just write kf. I'm really sort of emphasizing the math operations here, so I'm not leaving out any symbols. I'm going to go ahead and put the dot. As we move forward and I'm actually doing the math, sometimes I will omit that dot. So the limit of a constant times a function is equal to the constant times the limit. And again, since we know what the limit is, we can just say K times L, right? Make sure it's the right letter. If we're using F, well, then this is L. All right. And then I'll put a little side note here. This property applies to all functions. So in particular, it applies to G. So this property also applies to the other function. I'm not going to write it down as a new property. Just replace all the F's with G's, and then replace the L with M, because the limit of G is M. Now, before I erase these, and I'm going to give you a minute to write all this down, I just want to talk a little bit about the word property, because we use this word quite a bit in math, generally, all levels of math. When I was in college, 30-some years ago, we sometimes referred to these as laws, okay? And in fact, textbooks, older textbooks, from the 20th century would often refer to these as limit laws. In fact, that's the way I learned them. Learn your limit laws, right? And there are 9 limit laws. Some books have 10. They might combine some. Some books have 8. They're basically the same laws, just rearranged in a different order, in a different numerical pattern or numerical list. But we call them limit laws, right? And as a young student, aspiring mathematician, I just learned the laws because I was told to memorize the laws and make sure I knew my laws and follow the law, right? And it sounded very authoritative, and you got to do what the law tells you to do, right? But as I matured and as I got more educated and eventually became a professor myself, I realized that in some books they don't call them laws; they call them properties. Depends on who wrote the text. And I thought about that for a minute. A property has a completely different connotation than a law, right? I mean, a property is something that just is, right? And I started to think about it a little bit, and when I'm teaching, I want to make it very clear that a property can be thought of as a law. You must do this. Yeah. So a law must be followed. Yeah. If we called it a law, which is the way I was raised. Yeah. You must follow the law. But a property can be applied. Right? You have permission. And it's a much different way of thinking about what a property is. And so that is the emphasis that I'm going to place on properties, is I am saying, sure, if you want to think of these as laws, that's fine. These are things that you must do. Yeah, that is certainly one way of thinking about it. But I like to think about it in a different way. I like to think about this as a permission to do these things. I can do these things. I am allowed to do these things, which makes it seem much more important than a law. These are your rights. Yeah. You have the right to do these 5 things, and I'm about to give you 4 more rights. So when I'm done here, you'll have 9 rights. That's your calculus bill of rights. So for the entire course, whenever we see a problem, you come across an algebra or a calculus problem. Again, we'll call it a calculus problem, but notice that a lot of this is very algebraic in nature. You can do these 5 things. Yeah. All right, hopefully while I was talking, you got these ones written down. All right, I have them all down in a nice little list here that I'll be referring to throughout the examples. I better get the rest of them on the board so that you can actually learn how to use the properties. So there's 6, property number 6 is the product property. Very similar to the sum and the difference property. If you have the product of two functions, you can distribute the limit to each of the functions. Yeah. That's actually interesting because in algebra, there's no such thing. So if you said, A times B times C in algebra, now if these were not limits, these was algebra, it would not be A times B and A times C, right? It would just be A times B and then times C. Yeah. Or you could use one of the other properties, A times C and then times B. So you don't get, this is not equal to AB times AC. This is not true in algebra. But in calculus, right, this is a limit, right? And so a limit, it is true. The limit of FG is the limit of F times the limit of G. And again, since we know what these limits are, we know that F, the limit is L, and for G, the limit is M. We know that that's true. Property number 7 is sometimes called the quotient property. F of x over g of x. I'm using the brackets just as a grouping symbol, just to group them together. They're not really required. If you wrote them without the brackets, the property would still be true. This would be the limit of f over the limit of g. Now this one does have a caveat. M cannot be equal to 0. Going back to my warm-up intro non-example or whatever, I guess you could call that warm-up problem example 0. I'm going to start very soon with an example. You can't have the denominator be 0. The numerator can. Yeah. So 0 on top is fine, but 0 on the bottom is not okay. 2 more, sometimes called the power property. So we have product, quotient, power. The power property, we can take the limit of the function and then raise the answer to the power, whatever the limit happens to be. So it's kind of thought of as just taking the limit and putting it inside the brackets and then calculating the limit, and then after you're done, calculating the power. All right. Now again, we know that this function is f, so we know the limit is L, and then the power is n. This one's interesting because typically when you write a power, you think of it as, 1, 2, 3, 4, 5. But powers could be any number. They don't have to be nice whole numbers. But in order for this property to be true, they have to be the ones that you learned in elementary school. So n has to be 1, 2, 3, 4, etc. In other words, a positive integer. So this property is not necessarily true if the power was a decimal, like 0.5, or a negative number, -1. This property may or may not be true. Right? It's not guaranteed to be true. So just think of this just like elementary school powers, first power, second power, third power, things like that. Also known as whole numbers. And your 9th and final property is the root property. Very similar to the power property. With a root, we don't need the grouping symbol because the root is its own grouping symbol. So you can just take the limit and put it inside of the root. All right. And again, since we know that f of x has a limit called L, we can calculate the nth root of L. And again, this property is only true under certain circumstances. You remember from basic algebra, if the root is even, then the inside must be positive. So you can't, we're not allowing imaginary numbers in this course. Right? They shouldn't occur. Yeah, that's a complex analysis or calculus of complex numbers or imaginary number, the study of that we're not going to engage in. So if you're taking a square root or a fourth root or any other exotic or any other even root, I was going to call them exotic. They're just pretty standard even roots. Then the radicand or the inside of the radical must be positive. So that clears all that up. I always wished we could do 10. I mean, I could probably make a 10th one by tweaking some of the other ones or maybe, something like that. But there's just 9. There's 9 properties. Right? Which is kind of neat. 9's a cool number. And then I will also make the same comment I made earlier. These are true for any function. So number 8, you could replace f with g, and then you would replace L with m, because g is a different function. Like the names of the functions really don't matter. I'm just using 2 very standard names, f and g. All right, well, I tried to keep that short. That's half an hour to get through that, and that's with me doing the numeric tables before I pressed record. So we'd probably already be at an hour now if I hadn't done that. There's 2 ways of looking at this. One way is I could have just taken a piece of paper that had the properties written out and said, okay, there it is. There's your properties. Let's move on. That is one approach, and there are people that use that approach. I don't think that it's very helpful. It was never very helpful for me. I like to hear the properties and see them written out, and each time a property is given, understand what it's actually telling me, as opposed to just being handed a list and saying, here's the rules. All right, good luck. Well, now I've done that. So I've spent the last 20 or 30 minutes explaining the 9 properties. These are your permissions. You have the right to do these 9 things. So let's go ahead and exercise our rights. And I usually keep a copy of them handy, just look over at them, make sure you're using them properly, make sure you understand what you're actually doing with the properties. Finally, we get to the examples. All right. So the graphs of f and g are given. Go back to some graphing. And I'm using the shorthand notation, just calling them f and g instead of f of x or y equals f of x or what have you. So use the graphs and the properties to compute the limits. And I'll write out a list of limits. All right, so this is, I really probably should have prepared these graphs ahead of time, but I didn't have time to press pause in order to do that. This is something that probably should have been prefabricated. awful silence. All right, so this is f. So that's the blue parabola. All right. And then G. G is the red line. All right. So let's calculate some limits. Let's do the limit as x approaches 1 of f of x plus g of x. Okay, and so I might have mentioned this in my previous graphing problems. I don't always show solid dots like that. You won't see them as solid dots. So you are to assume, if you do not see any holes in a graph, that there are no holes. And you're also to assume that every point on the graph is, in fact, a solid dot. But it might help you. Again, this is an online format, so you're looking at this on a computer screen. If this were the in-person version, I would, draw this on the board, or students might have some graph paper. I like just adding a little, critical value here. All right. Now we're not worried about the left and the right. All of the properties that I just talked about apply to both left and right limits. Otherwise, there would be 9 more properties for the left and 9 more for the right. We're just looking at the general limit as x approaches 1. All right. So this looks like 1 here. X approaches 1. I'm assuming it's a unit scale. So I'm going to find the critical value for f. So the limit as x approaches 1 of f is 0. So as the function gets close to 1, the value of the function gets close to 0. And then down here, I'm looking at g, 1, 2, 3, 4, negative 4. The limit as x approaches 1 of g is negative 4. So using the property, this is the limit of f plus the limit of g, which is 0 plus negative 4. So the result is negative 4. All right. Let's do the limit as x approaches negative 1 of f of x minus g of x. All right. So sometimes I use the same number every time, but I don't want to have to redraw this graph, for 5 more examples. So I'm just going to use one graph and do various different values of x. Okay. So let's move over here to negative 1. All right. There's a point here. I'm just sort of emphasizing that point. The limit as x approaches negative 1 of f of x is 1, 2, 3, 4. Positive 4. It's probably no surprise, based on what we did in the last couple lectures, that when there is a solid dot or a point on the graph, the limit is equal to that point, right? It's kind of like those graphs I drew where I had a hole and then I filled in the hole. And So if the hole is filled into the limit, then the limit is the same as the value of the function. Since this lecture is all about limits, I'm focusing on the limit terminology and the properties of limits. Let's come down here to g. That looks like -2. So the limit as x approaches -1 of g is -2. You get that? My head is in the way. So the limit property says that I can take the limit of the difference. So first do f minus g. I do need to be a little bit careful. The limit for f was 4. And the limit for g is -2. Double negative. I'm going to use some parentheses. So the result is 6. 4 plus 2 is 6. All right. Take a quick look at that before I erase anything. I'm going to keep my graph and do a few more limits. Let's call this C and D. Let's do the limit as x approaches 0 of f g. And we'll also, I might as well get them both out here at the same time. The last part will be the quotient. I don't really need the brackets for the quotient. You could, might as well. I'll put them. Might as well be consistent. You really don't need the brackets for any of these. It's just to be clear that the limit is applying to both of these. All right, so I've kind of gone all around the different x values to sort of show how to do the limits. You should be looking at the critical values. So when x approaches 0, that's right here on the axis. The limit as x approaches 0 of f of x is 3. And the limit as x approaches 0, let me get rid of my old critical values. Make sure we're focusing on the right points. So these are the 2 points I'm concerned with. That looks like -3. There's +3. I'm just keeping the 1s on there for a scale measure. So for g of x, it's -3. You could probably just jump right to the answer. It's going to be 3 times -3, which is -9. I have all this empty space, and it's not a bad idea to learn the language of math. So it's the limit of f of x times the limit of g of x. I mean, good form is important, is a good answer. This limit is 3. This limit is -3. The dot's really not necessary, but it's already there, so -9. All right. And one more part. The limit of, as x approaches -2 now, so we're over here at -2. So the limit as x approaches -2 of f is also 3. Yeah, it's the same y value. And then down here, the limit as x approaches -2 of g of x looks like -1. It's the y value at that point. Okay. So again, I probably could just jump to the answer. It's going to be 3 divided by -1. So I already know it's going to be -3. But just to show good form, I'm going to use the property x goes to -2 of f divided by the limit as x goes to -2 of g. I do have to make sure g is not 0. It's not. It's -1. And then f is 3, and so the limit is -3. So this is like the collision of algebra, geometry, arithmetic, and then using a limit, it's calculus. Yeah, so we're sort of, all of these things are sort of coming together to form one subject, which, I just call it math. I mean, it really is just math. We like to label things to help you stay on track, where you are in your education, but ultimately we're creating a holistic subject, just mathematics. Okay. The graphs take up a lot of space, so for the rest of these examples, I won't use the graph. That was sort of the combination of the graphical and the algebraic. Oftentimes we do algebra without actually seeing the graph. One of the big lessons that will be coming in future chapters, might happen a little bit more in this chapter as well, but it's really going to get intense in chapter 2 and 3, is we do the whole problem blindly, without actually seeing the graph, and then we use all the information that we gathered to draw a picture. It's sort of like, feeling it out and going, and then, once you have a good feel for what you're doing, then you can represent it visually, right? Imagine it in your mind and then draw the picture. We're not quite there yet. So for the rest of these, no graphs, all right? I'm just going to do it all numerically. And we could have probably started with these and whipped through a whole bunch of examples, but now that we've gone through the introduction and the properties and a long graphing problem, now we can just fly through the rest of these problems, all right, using the properties. So suppose that we are given two limits. Now they do have to be approaching the same number, all right? Notice all of the properties, sometimes, and I'll have to admit, when I was in college, I would just be lazy and write down the limits like that, And I see that a lot, especially in my in-person class where I'm collecting, things on paper, and I'll always make a comment that it's okay in your notes, but it's very dangerous because not all limits have the same, value that you're approaching. So you do have to make sure that they are, in fact, approaching the same value. Now, once you're confident that they are, it's okay in your notes to, change those values or something. Or to omit those values, sorry, not change them. Definitely don't change them, but you can omit them in your notes, right? If it makes it easier for you to follow along, you just write lim. Right? I do it all the time. Lim, 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 lim. And then when I get to the very end, I put that back so that I don't forget what value it's actually approaching. Okay, apply the properties. To determine, another way to say calculate or compute the limits. All right, so how about the limit as x approaches 8 of 2 f of x plus 3 g of x? Now, when I first learned this, I thought, oh man, really? That's calculus? Why'd they make us wait so long to do calculus, right? Because, mental math, you would just say, 2 times 6 is 12, 3 times 5 is 15, 12 plus 15 is 27, and I write the answer 27 and I'm done. Didn't need any calculus, right? Where does the calculus come in? Well, the calculus is all about the properties, right? And we may not always be given these values. And so when we simply do the quick and easy solution, sure, we get the answer, right? I mean, I'll give you that. We're done. The answer is 27, right? But that's arithmetic, right? That's not calculus yet. So the calculus comes in exercising the properties, and then learning them so well that when the problems get harder, which they will, you will be so good at applying the properties that you will just do it naturally, right? As opposed to simply, because it's not always going to be as easy as just multiplying and adding. So go ahead, write that down in your notes. The answer will be 27, but I'm going to go ahead and use the properties. All right. So this is going to be lim x goes to 8 of 2f of x. Now that's 2 times f of x plus lim x goes to 8, approaches 8 of 3g of x. Which is, again, so that's the product, that's the sum. Limit of the sum is the sum of the limits. And then now we have a constant. This is like the k. They're different k's. This is like k1 and k2. But those are your constants. I like to spell constant with a K when I'm using the letter K. When I'm using the letter C, I like to spell constant with a C. So what's the property? It was property, I don't know. I could make you tell me what property it is. It was property 5, right? So the first one is property 3, and then property 5. I can pull the constant out in front. It's going to be a tough pill to swallow because, you've got better things to do than this, but maybe do you? This is calculus, right? We're exercising the properties of calculus. And then someday you won't know that it's 6 and you won't know that it's 5. It won't be given to you in the problem. And so understanding the properties, when the day comes that we don't know what these are, the properties will really help seal the deal here. It also prevents mistakes. And there's the 27 we predicted a minute ago. Okay, so sure. Use mental math to predict what it's going to be. But if you're here to learn calculus, which I assume you are, otherwise you wouldn't have signed up for this course, then this is the steps of calculus. All right. When I took this course, 30, God, how many years ago? 35 years ago. I took this course 35 years ago. My instructor would make me write by property 5 or by property 3, by property 5, whatever. You had to dictate or annotate each property. Otherwise, you were not given credit for that line. And you would definitely not be given credit for the final answer. All right, there was no internet back in 1989. Paper, pencil, pen, what have you. All right. I'm making myself seem old now, so let me move on. That's A. Do I have room for a B? Probably. How about the limit of 4 minus 4 f of x. All right. I'm going to need to borrow this space here, so let's just put the answer over here so I can have this space back. All right, so this was 2 times 6 plus 3 times 5 equals 27, in case you're still catching up in the video. You can press pause anytime you need to. I'm sure you all know that. All right, so again, this is the property 4. Limit of the difference is the difference of the limits. So this is the limit as x approaches 8 of 4 minus, now you can combine two properties to save a little space. This is property 5. So first I used property 4. Now I'm using property 5 and property, just property 5. 4 times the limit as x goes to 8 of f of x. The constant property is actually one of the more important properties, right? The limit as x approaches 8 of 4 is just 4. That's property number 1. Yeah. The limit as x approaches any number, doesn't matter that that's 8, because the 4 is a constant, it doesn't have a variable, right? It is technically a function. It's just a very boring function. It doesn't change. It's always equal to 4. All right. And then 4 times the limit here, which was 6. So that's 4 minus 24, which would be negative 20. I love putting this kind of problem on a test because I always, preach this mathematical philosophy about, even if you know the answer, do the steps anyway, right? And that's hard for people to get used to. But I've been teaching math for a long time, and I see what human beings do. And one of the most common mistakes, even for a calculus student, it's just this tendency to sort of switch back to your childhood and go 4 minus 4 equals 0, and then you just get the whole thing wrong, right? So it's not 4 minus 4, it's 4 minus 4 times 6. So 4 times 6 is 24, so the answer is negative 20. All right, so we got room for a couple more. I'm really starting to run long on time here. Yeah, we could do a C and a D. The limit as x approaches 8. Now again, we can only do as x approaches 8 because that's all we know. Of 9 f of x plus 2g of x divided by g of x. 45. Yeah, good. Yeah, that's fine. I'm not going to change it. It might not be pretty, but we'll see what it is. All right. So just to exercise the properties, first we have a quotient. So we have the limit of 9 f of x plus 2g of x. Then we have that's supposed to be an 8. See, here's where I'm starting to get lazy. I just want to write lim, which in your notes you can. Just in the back of your mind, make sure you know it's 8. of g. So first you do the quotient, right? Quotient sort of is, it's the first grouping symbol that you see. Then you do the rest of them. If I can squeeze them all in here. And I'm going to combine a couple. So this is the limit of the sum. And then it's also a constant and another constant. So it's going to be 9 lim f plus 2 lim g. I'm showing you how even I break or stretch the rules a little bit. I'm only doing this because of time and space. So this is lim x approaches 8. That's lim x approaches 8. That's lim x approaches 8. And I'm just sort of being very loose with the notation there. And let's see if I can finish that. I'm running out of space. I hate when that happens. So we know that we have these two limits. So this is c continued. So I've got 9 times 6 plus 2 times 5 divided by 5, which is 54 plus 10 divided by 5, 64 fifths. I can't reduce this. That's why I paused a minute ago. It doesn't really matter. I just want it to be correct. So we'll reduce that if possible. It's not possible, so 64 fifths is the answer. I don't know what numbers you're going to get. I sort of randomly select values, and sometimes I get nice whole numbers. Sometimes I get negative numbers. Sometimes I get irreducible fractions. Sometimes you get reducible fractions. I considered making the denominator f, and then which I didn't. So that's why, once I made it g, that was it. It's g. But had I chose the other path, had I chose the denominator to be f, then it would be 64 sixths, which would be reducible. Yeah, it'd be like 32 thirds or something. So reduce only if possible. All right, so I know this is getting exhausting. I'm almost done. Hopefully I can get this all done in 10 minutes or so. You'll see that it does get easier as we go along. So let's do part D. Part D is the lim as x approaches 8. Of 3f of x negative g of x. And I've got an extra set of parentheses here to be very, very careful. I intentionally kept this problem written exactly the way it would be in the textbook or in the homework or on a quiz, or no, there's no quizzes, or on a chapter test. I used to give quizzes, but chapter tests will be plenty to keep, and the homework will be plenty to keep you busy. So this is not subtraction, right? That's multiplication. So I just want to make a quick note of that before we move on. This is an invisible multiplication by -1. All right, I'm actually going to make it visible in a second. So we have several properties here. The first property we can use is to bring the constant outside. I like to do that first. And then now whatever I get, I just multiply that by 3, and that will be my result. And now I got to be careful, okay? This is an invisible -1. Yeah. So this is going to be the limit as x approaches 8 of f of x times an invisible -1 times the limit. Well, first it's just going to be g of x. Then it's going to be the limit of f of x, right? And then times another constant comes out, and then the limit of g of x. So I'm multiplying by -1. I'm not subtracting there, which is very important. And now I can put everybody in. This is 3 times 6 times, and you could put dots between everybody if you wanted to, times 5. Just to make sure that you don't accidentally subtract. You don't really need the dots. If you don't use dots, you should probably butt the parentheses up against each other so that there's no gaps. I'm a big fan of good form. It's one of the things I miss about teaching this class in person, is where I could, see what you're actually writing. If you come see me on Zoom, maybe share with me what you're actually doing. That'd be great. I don't have an effective, efficient way of having you give me your writing. You just give me the results, and I hope that you're writing this out nicely. 3 times 6 is 18. -1 times 5 is -5. I'm just going to use a calculator because I'm tired. -5 times 18 is -90. And that is the end of that example. All right. The last couple examples, man, was that really only 1, 2 examples and a big long intro? That's Dr. Jordan for you. I like this stuff, so I can talk about it all day long. Example 3. Instead of being given a limit, you're given the actual functions themselves. Once we do this example, we will be able to fly through a lot of these problems, because this is what we call evaluating now, which is much faster than applying properties of the limits. So this is what really brings algebra and calculus together. Is that clear? That's x squared, and that's a -6. Okay. All right, so I'm interested in a couple. I'm going to do all the same limit here again. So the limit of, as x goes to 6, of f of x. All right. So now that we've seen the properties, you've written them all down, you saw me exhaustively go through every step by step. This is what we just call direct substitution. All right. So the properties allow what's called direct substitution. Now you do have to do it carefully, because you have to make sure that you're not violating any of the properties. So I have a constant. I have an x. Yeah. So I can pull the constant out, and then I can apply the limit to the x. But property number 2 says when you apply a limit to an x, you just replace the x with whatever the limiting value is, which in this case is 6. That's property number 2. Yeah. The limit as x approaches c of x is equal to c. So the limit as x approaches 6 of x is 6. Yeah. So this is the property number 2. Right? If I were making you justify your answer. And then -7. Yeah, the limit of a constant is a constant. So on a day-to-day exercise, or when you're going through your homework, this is how you're going to do it. You're going to read the limit, you're going to look at the properties, and you're going to apply direct substitution. You do have to do it carefully. So 7 times 6 is 42 over 6, which is 7 minus 7, which is 0. Yeah. I guess another way to do this, if you're an algebra master, you could have just canceled the 6's. But I mean, be careful. That 6 is not in the bottom. It's in the top. It's technically 6 over 1. Again, I get carried away with my algebra because and I've graded a lot of papers in my time, and that's where all the mistakes lie. So here we go. The limit as x approaches 6 of g of x. Well, x squared. Well, there's an x, so it's going to be 6. We have the power property, which was property 8. The power is 2, so you just take the power of the limit. Okay, minus the constant times the limit. So that's 36 minus 36 minus 7, which is negative 7. Not too shabby, huh? Now watch this. Look how quickly we can do these now. F of x over g of x. In the interest of time, I'm omitting the brackets, right? There's brackets here. Well, we already know the limit of f is 0. We already know the limit of g is negative 7. It's okay that there's a 0 on the top, and as long as there's no 0 on the bottom, the result is 0. But to emphasize the quotient property when the 0 is on the bottom, if I reverse it, g over f, well, you got to be careful. So I apply the properties carefully. Negative 7 divided by 0 is dne. Does not exist. So that limit does not exist. If you just give me about 3 more minutes, I'll do a few more examples so that you can finish your homework exercises easily. I think I've probably shown enough here, but I just want to make sure that we can sum up all the properties very quickly. So take a quick look at that. Make sure you understand how I'm doing this. Direct substitution. Direct substitution is just taking the properties and directly applying them into the functions. And that's what we'll do for the rest of these examples. All right, example 4. F of x equals 9. Find the limit as x approaches negative 2 of f of x. And use the properties. All right, so this is the limit as x approaches negative 2 of 9. Yeah, directly substituting, the f of x is 9. This is a constant, so the answer is still 9. These will go quickly. How about f of x is 5x? Find the limit as x goes to 3 of f of x. Okay, again, directly substituting. We have the limit as x goes to 3 of 5x. Which is 5 times the limit as x goes to 3 of x. I don't really need to write that step. I'm not going to. I'm going to take that back. The parentheses are just going to be 3. Yeah. The limit as x goes to 3 of x. Put that in my cloud there. That's property 2. So it's 5 times 3, so the result is 15. And you can do this with any function as long as it doesn't violate any of the properties. Yeah, so you can apply them. like you naturally would. Just be careful that you're not breaking any of the laws, I guess. There I go again. Yeah. Example 6. F of x is 5x squared minus x plus 4. Find the limit as x goes to -2, not -2, -1, I already did -2, of f of x. Because I'm running out of space, what I'm going to do is do the math over here, yeah? 5 times -1 squared minus -1 plus 4. So this is sort of my scratch work over here, which is 5 times 1 plus 1 plus 4. 5 plus 1 plus 4 is 10. All right. Directly substituting the limit for the value of the function. Essentially what this means is f of -1, the value of the function is 10. Remember the definition of limit? The limit is also 10. So this function sort of looks like this. The limit is telling you that it's getting very close to 10, but because the value is also 10, the value fills in the hole, and so the limit and the function are agreeing with each other, and we are directly substituting the limit for the value of the function. All right, as long as it's defined, you can do that. How about this one? The limit as x goes to 3 of x squared minus x minus 8 over x minus 3. Okay, so this is your function here. I'm just not using the f notation. I'm just calling that the function. Well, again, you can directly substitute 3 in. I'm going to move over here. As soon as you see that you see 0 on the bottom, stop. You really don't have to continue working out the top. You're going to get DNE. All right. So this is very similar. It's sort of upside down, but this is a reciprocal or rational function. Very similar to the first thing that I did today when I made the table of values. I'm not going to do that again, but it's getting very close to 3, but not actually equaling 3. And then the values do not approach any particular number. They just end up either going to infinity or negative infinity. I would have to make a table to determine which it was. If it was, are they both? There's a couple possibilities. They could both go up to infinity. They could both go down to infinity. Or you could have one going up, one going down, or the opposite, one going down, one going up. I'm already done. This is going to be my last example. But when you get 0 in the denominator, that's an indicator of the behavior of the function. It's either going to be a whole or an asymptote. Again, I'd have to make a chart to figure that out. Although, because the limit doesn't exist, I tend to believe it's an asymptote. Yeah. If it was a whole, then the limit may exist, but the value is not the same as the whole. But I digress, and I'll do the last one. The limit as x approaches 2 of the square root of x squared minus 4x plus 9. So again, this will be the square root of the limit. I do have to be careful that I don't get a negative number, otherwise it would be dne. Directly substituting, I get 2 squared minus 4 times 2 plus 9. 4 minus 8 plus 9. Square root of 5. Simplify if possible. Don't use a calculator unless instructed to do so. The square root of 5 would require a decimal. We want the exact value. So the exact value is an irrational number. So just leave it square root of 5. Well, about 5 or 6 minutes longer than I intended, but you know, it was necessary so that we could be done with this section. We got more coming, so tune in again tomorrow. But until then, I'm Dr. Jordan, and I'll see you on the internet.